Yesterday we talked about the work energy theorem application on a system of particles, which states that sum of work done by all forces acting on the system from outside and from inside is equal to change in kinetic energy of the system of particles. Let us now assume that on the system of particles, no force acts from outside. This means all forces are internal forces. All forces are internal forces. If this is the case, if the external force acting on the system is equal to 0, work done by the external force will be 0. According to work energy theorem, work done by the external force plus work done by the internal forces, that is the net work done, is equal to change in kinetic energy of the system of particle. And if external force does not perform any work, then internal force may perform some work, that will be equal to change in kinetic energy. If the internal forces are conservative in nature, work done by the internal forces is the work done by the conservative forces, is equal to negative of change in its potential energy. You know that in a conservative force field, the conservative forces perform work at the expense of the potential energy of that field. For instance, I take this pen, I lower it. While doing so, gravity is pulling it down. This body comes down, gravity also pulls it down. So, gravitational force does a positive work because the gravitational force and the displacement both are having same direction, downward direction. Therefore, the work done by gravity is positive, and that is equal to mg into h. Work done by gravity, when you lower an object through a distance h, gravitational force is mj downward, displacement is equal to h downward. Therefore, work done by gravity equal to mg into h positive. While the body is undergoing a displacement, downward displacement h, what is the change of gravitational potential energy? The change in gravitational potential energy is equal to minus mgh, because initial potential energy is mgh1, final potential energy is mgh2. Change in potential energy equal to final potential energy minus initial potential energy. What is final potential energy? mg into h2. What is initial potential energy? mg into h1. This is equal to mj minus h1 minus h2. And h1 minus h2 can be written as h. Now you understood why I wrote change in potential as is minus mgh. Change is always final minus initial. This is the initial position, this is the final position. Initial position I, or you can write 1. Final position F, or you can write 2. When a body comes down, the gravitational potential energy change is negative, minus mgh, and the gravitational work done is equal to plus mgh. So they are exactly equal and negative to each other. Therefore, you can write work done by gravity equal to negative of change in potential energy. Work done by any conservative force is equal to negative of change in its potential energy. If we accept this theorem, whose proof I have given through this example, then using this two equations, I can write minus del u instead of work done by the internal force is equal to del k. This gives us the idea that change in potential energy plus change in kinetic energy will be equal to 0. Or you can write change in total energy equal to 0, or you can write total mechanical energy remains conserved. This is what we call conservation of energy, means mechanical energy of the system of particles. What is the condition for that? The external force acting on the system will be equal to 0, or even though they are present, they must not perform any work. Condition is that work done by the external forces must be 0. In that case, there is a possibility of conservation of mechanical energy. And second condition, the internal forces must be conservative. There are two conditions. Condition number 1, external forces may be 0, or even though external forces are not 0, they must perform 0 work. Second condition is that the internal forces must be conservative. Under these two conditions, we can conserve the mechanical energy of a system of particles. This is a very great idea of conservation of mechanical energy applied for system of particles under these two conditions. So I will glorify this idea through a simple example. Let us take two examples. Example of two block system. Here block 1 and block 2. Block 2 is placed on a smooth horizontal floor. Between the block 1 and 2, friction is present, such that friction acts on the block 1 in forward direction, in positive x direction, and friction acts on the block 2 in negative x direction. Let us assume that the block 1 has displacement ds1 and block 2 has displacement ds2. Yesterday, we discussed this problem to prove that work done by frictional force on the first body, first block, plus work done by the frictional force on the second block is equal to F into S1 plus work done by the friction on the second block. Frictional force is oppositely directed with respect to the displacement, therefore it is minus F into S2. In this you are getting minus F S2 minus S1. You can write minus F into S, where S is the displacement of the block 1 with respect to the block 2. In this way you can understand that net work done by the internal force is not equal to 0, because this is not equal to 0. Hence, change in kinetic energy plus change in potential energy cannot be equal to 0. In this case, change in potential energy, gravitational potential energy will be 0, because these bodies do not change their heights. This block is at this height H1, this block is at a height has to the center mass of this blocks. Therefore, the change in gravitational potential energy will be 0. Hence, the kinetic energy change will not be equal to 0. This means that the system or the system's kinetic energy or mechanical energy does not remain constant. In other words, we can say that we cannot apply the conservation of mechanical energy for the system. You cannot conserve the mechanical energy of the system where the internal forces are kinetic force of friction. Question is, can you apply mechanical energy conservation principle Can you apply mechanical energy conservation principle? For this two block system, if the frictional forces are kinetic force of friction? The answer is no. Why? Because the work done by the internal forces is not equal to 0. And the internal forces are non-conservative in nature. The work done by the internal forces is not equal to 0, or you can say negative, and these forces are non-conservative. So this system is a conservative system, because frictional force, kinetic force of friction is non-conservative force. Therefore, we cannot apply the principle of conservation of mechanical energy for this system. Now come to another system. Block number 1 is placed on the prismatic block, or you can call it wedge 2. Here, can you apply conservation of mechanical energy for the system? Conceptual question. Assuming no friction between 1 and 2 and 2 and ground. When there is no friction, work done by the non-conservative force is equal to 0. Now draw the FBD. Gravitational force M1G acts on the block 1. Gravitational force M2G acts on the block 2. Block 1 is touching the block 2. Therefore, on block 1, normal reaction N1 acts. On block or wedge number 2, the normal reaction N2 acts. These two forces are called constraint forces, because these two forces are arising due to the contact of these two bodies, and there is no relative motion along the line of application of these two forces. Therefore, we can call these forces constraint forces. Let us calculate the work done by this constant force N1 plus work done by this constant force N2 plus work done by another constant force, that is the normal reaction offered by the ground onto the wedge, N3 plus work done by gravity force M1G on the first block plus work done by this gravity force M2G acting on the wedge. Sum of all the work done is equal to change in kinetic energy. That is our work energy principle. Since these gravitational forces are conservative forces, these two forces are conservative in nature, and work done by the conservative force is equal to change in potential energy of the system. So, instead of these two factors, I can write change in potential energy of this block 1 here minus of or negative of the change in potential energy of the block number 2 or wedge is equal to del K. Del K means change in kinetic energy of the first body plus change in kinetic energy of the second body. So, this factor is change in potential energy factor, this factor is change in kinetic energy factor, and this is the work done by the normal reactions. Since this normal reaction N3 is perpendicular to the displacement of the wedge worked by normal reaction N3 will be 0. Let us assume that block 1 has displacement ds1. Therefore, work done by the normal reaction N1 on block 1 can be written as N1 dot this normal reaction of the action reaction pair N1 N2 acts on the wedge. The wedge displacement is ds2. Therefore, normal reaction N2 does a work N2 dot ds2. Minus del u1 minus del u2 equal del k1 plus del k2. Next step we can write displacement of the first block with respect to ground equal to displacement of the first block with respect to the second, the wedge, plus displacement of the wedge, because displacement of the block 1 minus displacement of the wedge is equal to displacement of the block with respect to the wedge. Galilean transformation of displacement, velocity and acceleration. Therefore, displacement of the block, that's ds1 equal to ds2 plus ds12. These are all vector quantities. So, you have to put arrows. Therefore, I wrote ds1 equal to ds12 plus ds2. This is n1 vector plus n2 ds2 minus del u equal to del k. The next step, you can just rearrange. Here ds2, here ds2. Take it out of or take it common. You are getting n1 plus n2 dot ds2. In the first term, n1 dot ds12 minus del u equal to del k. You can note that n1 plus n2 is always equal to 0 because they are action reaction pair. And ds12 means, what the physical significance of ds12? Displacement of the block 1 with respect to the wedge 2. This means that when you are standing on the wedge, you can see that the block is undergoing displacement either in this direction or in this direction, because with respect to the wedge, the block cannot move in this direction. So, only one direction it can move, either towards down or towards up or along the wedge. So, I can assume that the block moves with respect to the wedge in this direction, and this is perpendicular to n1 vector. Therefore, n1 dot ds12 is always 0. In this way, I can prove that minus del u equal to del k, or we can just write del u plus del k is equal to 0. This means that we can conserve mechanical energy for this system of the block and the wedge. For this web block system, we can conserve the mechanical energy. Can you apply the conservation of mechanical energy for the system? Oh yes. This is the answer. Yes.